Okay, I'd like to start another tutorial. In this tutorial, we're going to look at a DC response of an op-amp circuit. Previously, we looked at just a DC circuit, but let's look at a DC circuit analysis of a circuit including an op-amp. So what I'm going to do is work in the same project. And so we'll go back to the project. And under schematic, I'm going to create a new page. And let's go ahead and call this new page problem 5.6, because I'm going to do problem 5.6 in Nielsen's textbook. And so I'll go to the schematic for problem 5.6. I double-clicked on it to open it. And what I want to do is we're going to build an op-amp circuit that's going to represent the circuit here in problem 5.6. So we're going to start again by placing parts on our schematic. So I'll place a ground on here. We always have to have a ground. And in this, we have an op-amp. And the op-amp has rail voltages of plus or minus 15. What we're going to do is we're going to use an ideal, the Orcad's representation of an ideal op-amp. It actually is not specifically ideal. It's an analog device. So I'm going to type in op-amp. It has a circuit model for it, which really is invisible to us. But internal to this op-amp actually is a 15 volt plus or minus 15 volt rail voltage. So that plays in well, but we know that going in. So I'm going to put in an op-amp. Now, when I put in the op-amp, let me zoom in on this a little bit, because what I want to show you is that the op-amp shows that the non-inverting terminals on top and the inverting terminals on bottom, whereas the circuit that we want to build has a non-inverting up top, inverting at the bottom. So the first thing I'm going to do is I can't just rotate this, because if I rotate the op-amp, it's just going to like turn it the other way. But what I can do is right-click on it and do a mirror vertically, and it just flips it, does a vertical flip about its center axis, and now that flipped the minus sign at the bottom and the plus sign at the top. So now I'm non-inverting the bottom and the inverting terminals up top. So at this point I can start building the rest of the circuit. So I can put my resistances on. So we have our resistor, and I want to rotate with Control R. So I have this 8K ohm in series here. And I'm going to have the 60K ohm above. And next to that, a 30K ohm. And then I'm going to have a 40K ohm, which is running vertical. I'll put that there. And then finally I have my output over here. Okay. And to get rid of this, I'm going to put an escape. Okay. Next, let's go ahead and put on our source. So again, I'll do a V source. I'll type in VSRC under my parts window. And here it comes up with a V source. Double click that. And I'll put my source voltage there and hit escape to get rid of that part. Now I'm ready to wire up. So I'm going to wire source to the series resistor. Again, I click on the terminal, and then I click on the terminal I'm connecting to. Same thing for this resistor, and so on. Okay, and this is connected to the output, and this terminal is connected to ground. Okay. Now, what I could do is I could connect all these to ground like this, or I could add in other grounds, since they're all grounds of the same node. But basically, this represents the circuit topology of the op-amp circuit in problem 5.56. Now, one thing I'm missing is I am missing a ground right here, so I'm going to click on ground. And okay, so I'm going to choose my I'll put my ground right there. So that's 0, so that's the same node as this node here, which assumes that to be my reference node. And now that resistor is grounded. Okay, The next thing is, okay, I see these two resistors, a little bit of confusion as to which R belongs to who. When I click on this, I see the R10, this R highlight, so those belong to this resistor. I click on this, and this R and that R9 belong to this resistor. So what I can do is kind of, to avoid some confusion, I'm going to move these over here. And I'm going to move this up here and see if I did that right. I did. Okay. I'll move this up here. So now it's not confusing as to which value is which is related to which resistor. Remember, this R is the value, this R7 is the name. So I'll double click on the R, and this is an 8K ohm resistor, so I'll put 8K. This is a 60K. This is a 40K. This is a 30K. And this is a 20K. All right, so I've labeled my resistors. Again, I want a DC source. The source voltage is 240 millivolts. So I double click on DC, I can put 240M for millivolts. And I click OK. All right. So now I have all my components with the proper values on them for the resistances. Okay, so let's save this. And now that I've built the circuit, I can check my connection. So I have this is connected to ground. These are all grounds. This is 15045. So all these are common node. That's and so on. So I just double check to make sure that all my connections are correct. Okay. All right. Now we're ready to simulate. To do that, I'm going to go to PSpice and edit my profile, simulation profile, make sure I'm still in bias point. So that's good. And now what I can do is simulate this. So I can, again, under PSpice, run, click on Run, or I can do it down here on the main menu. Okay, so no errors came up. That's a good thing. I've analyzed this. Then I get my bias point values. So of course this node is 240 millivolts, which checks because that's that's the source. It's between this node and ground. This is still 0. This here is, even though it says 4.05 microvolts, okay, for all practical purposes that's 0. Again, this is not a truly, it's not an ideal op-amp. It's a model of an op-amp, and I expect that the voltage difference here to be very small, which it is. It's on the order of 10 to the minus 6 volts. Okay, so for all practical purposes, these are the same voltage. This voltage here is minus 1.8 volts. My output voltage is minus 4.05. Okay. Now over here in MathCAD, I went ahead and did a nodal analysis. And in this nodal analysis, this is my reference node, so this is 0 volts. This is 240. Those are my voltage constraints. My op-amp voltage constraint, of course, 0 volts across here. I called this VA, and this one V0. Okay. Now I can do nodal a KCL at 2 nodes. It have to be non-reference nodes, not connected to the output of the op-amp. That leaves 2 nodes. The node connected to the inverting terminal of the op-amp, and also node A are my 2 KCL nodes. I solve these two, I get minus 1.8 volts for node A and minus 4.05 for my output, which is exactly what SPICE predicts. Now, this problem you're asked to find the input current and also IA. I found IA to be 30 microamps, and that's just from VA minus 0 over 60 k ohms. Actually, going from left to right, it's 0 minus V over 60 k ohms. And that gives me 30 microamps, or 3 times 10 to the minus 5 amps. I also found I0 to be equal to the current flowing from A to 0 plus from VA to V0 plus the current flowing from reference to V0. Those by KCL will sum to give me I0. Those are the 2 currents, and that should be 2.7, basically 0.2775 milliamps. I'll come back to the solution here with Spice. And again, the currents are labeled so they're flowing from the node of that's connected to the other node. So I got 30 microamps flowing between the inverting terminal and node A. And that's exactly what we predicted with MathCAD. I have this current here is 75 microamps flowing from node A to the output. I have 202 microamps flowing up this way. So the sum of these two is 275 roughly microamps, which is exactly what we predicted using MathCAD. So again, that predicts, this validates the MathCAD prediction and vice versa. And I can look at the powers as well. Of course, my DC source is providing minus 7.2 microwatts. And again, I look at the net power supplied in the circuit, and this should add a 0. What's also interesting is my OpAmp itself is supplying 1.124 milliwatts, which accounts for the gain, which is seen at the output of 820 microwatts being delivered to this output resistance. Okay, so that is how we would analyze an OpAmp problem using PSpice.